Okay, hello everyone. You're all welcome to this video. I remain your tutor, Mr. Life Changer. And so in this video, I'm going to be going through the qualitative analysis aspect of the practicals for candidates that will be writing in 2026. There is so much to learn here, okay? And so I'm going to, from what we can see that the specimen for the quantitative analysis is supposed to be a mixture of lead carbonate, lead 2 carbonate, and starch. Okay, so in this particular video, I'm going to show you some of the properties of lead carbonate, starch, and some of the tests that can be used to distinguish them. Okay, now I'm going to start by talking about some of the reagents we are going to be using in this in the practicals. Now remember, the specimen, the mixture, though you are not supposed to know, but is a mixture of lead carbonate and starch. Okay, and some of the reagents you'll be given, you are going to be given barium chloride, you are going to be given silver nitrate, you are going to be given hydrochloric acid, you're going to be given H2SO4. You're also supposed to be given HNO3. Then you're going to be given dilute solution of sodium hydroxide and also aqueous ammonia, NH3AQ. And you are going to be given potassium iodide. Okay, so these are the reagents that you are going to be given. And each of these reagents have several effects or different effects on both, lead carbonate and starch. Okay, so a good example, for example, this test here, these ones here, these reagents from here to here are specifically for test for anions. Okay, they are used to test specifically for anions. Then while these ones here are used to test for cations. This is a special test, but I'm going to show you how these things go. Now the first one I will talk about is barium chloride. How barium chloride affects this. Now first of all, I want to say this, that both lead chloride and starch, both of them are insoluble in water, and because they are insoluble in water means that you cannot use water to separate them. So there is a likelihood that you will never see a case where you are asked to use water to separate these two, to add water. But if you are asked to add water, nothing spoil. But I'm trying to let you know that there is no particular, there is no way water can be used to separate this. Water can only be added maybe to prove, to try certain tests. So we are going to start with the solution of barium chloride on this. First of all, barium chloride does not have any effect on this. When you add barium chloride to a solution and you have a white precipitate, white precipitate actually indicates the presence of carbonate. It indicates the presence of SO4. It also indicates the presence of SO3 minus. Okay, so barium chloride, pouring barium chloride is going to indicate the presence of any of these. So that is not a major test. Now this is in drops. In drops. Now if you add barium chloride in excess and it dissolves, in this case now it is not going to dissolve, won't dissolve. Now the reason I know it's not going to dissolve, because I know that carbonate does not dissolve in excess barium chloride. So since it does not dissolve, it means that SO4 ion is not present. Okay, SO4 ion is not present. Or you can simply say that what is present is either carbonate or SO3 ion is present. Okay, so this is how barium chloride. That means barium chloride cannot be used to actually tell that carbonate is present there. This is how that ends. The same thing with AgNO3. Now AgNO3 is only used to test for halogens. Majorly halogens. Now, but if you add AgNO3 and you get a white precipitate, that white precipitate indicates the presence of carbonate and also of chloride, because chloride will give a white precipitate, chloride ion will give a white precipitate, carbonate will give a white precipitate, but this, it will not be a confirmatory test. It cannot give you a confirmatory test. Okay, now for the sake of HCl, and let me say this, these two agents does not have any effect on starch. They have no effect on starch. Okay, so the next is HCl. Now when you pour HCl, both HCl and H2SO4 and HNO3, the three of them are acids. When you pour them here, it most likely, especially in the case of HCl and H2SO4, an effervescence of gas will happen. Effervescence of gas, okay, will happen, and that effervescence that turns lime water milky. Okay, that turns lime water milky. It's going to turn lime water milky. Then that's because, you know, when lead carbonate combine with HCl, you are going to get lead, you know, chloride, then plus water and CO2. That CO2 giving off, this confirms the presence. Is a confirmatory test. Confirms the presence of CO2. Okay, that's very, very important in the presence of HCl. Now H2SO4 is also going to give you the same effect, effervescence of a gas, but the difference between H2SO4 and HCl, the difference between these two will be that H2SO4 will, if it is H2SO4, apart from the effervescence, you know, a precipitate will also be formed. Okay, a PPT will be formed, and that PPT is as a result of barium sulfate, because barium sulfate is also insoluble. You know, anytime you hear the word precipitate, it just indicates insoluble salt. So barium sulfate is an insoluble salt. So what that means is that in a case where H2SO4 is added, effervescence will happen and it will give rise to a gas that turns lime water milky. Now, but there will also be a formation of precipitate. This will not form a formation of precipitate for HCl, because if you combine HCl, you are going to get lead chloride, and lead chloride is actually soluble in water, right? Now, that's very, very important. Now, in the case of HNO3, like I said, the only difference between HNO3 and the two is that there won't necessarily be effervescence, but it will dissolve. Okay, that means the solution will dissolve partly. Solution dissolves partly in HNO3. So the solution dissolves partly in HNO3. Can you see that? And so that partly dissolution can indicate a lot of things. So adding HNO3 will only dissolve partly the solution, because lead carbonate can completely dissolve in HNO3 solution. Okay, will not necessarily give rise to CO2. So that is it for the test for anions. The next thing again is that you might be asked to heat the solution. If you heat the solution, of course, we're also going to have a gas given off. A gas is given off, and that gas given off turns lime water milky. The gas given off turns lime water milky. You can see that. Okay, so that's the effect of heat. In case you are asked to heat, maybe after pouring water or maybe after pouring HNO3, there will be heating will definitely, you know, give off heat. I mean, will definitely give off carbon 4 oxide. You can say here that CO2 is the gas. You can say CO2 is the gas, meaning that CO3 2- is confirmed. Okay, so those are the confirmatory tests. That means the confirmatory test of CO2 is either when you add an acid or when you heat it. In both cases, you are going to give off a gas that will turn lime water milky, and only CO2 is that gas that can turn lime water milky. I hope that makes sense. Okay, now for the case of cations, these three is what is responsible for testing of cations, okay? And if I start with, for example, sodium hydroxide, now if you add sodium, let me start with, sodium hydroxide in drops and in excess. In drops, okay? In drops and in excess. Now, when you add sodium hydroxide to a solution, you are going to get white PPT, white precipitate. If the precipitate is white, it means that the conformation, what this means is that you are either suspecting a lead ion or aluminum ion or zinc ion. And the reason is because the three of them are amphoteric. Only amphoteric ions, form white precipitates with sodium hydroxide. Then if it is in excess, if you drop in excess, the white precipitate, white PPT is sustained. That means it does not dissolve. Sustained means that you are suspecting either a lead ion or aluminum ion and not zinc. If it is zinc, zinc will dissolve in excess, right? If it is zinc, zinc will dissolve in excess, but the others do not dissolve in excess. That is very, 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 very important, okay? And so in the case of ammonia, in the case of aqueous ammonia, in drops, you are going to also have a white precipitate. Now, white precipitate here in the case of ammonia also indicates a presence of lead 2 ion, aluminum, and zinc ion, right? Then if it becomes in excess now, in this case, I know if it is zinc, only zinc is soluble in excess, okay? But the rest are insoluble in excess. So we are going to say insoluble in excess. Insoluble in excess because we are expecting lead ion, right? We know that it is lead, and lead is insoluble in excess this. And just for the sake of knowledge, the reason why zinc ion is soluble in excess this is because zinc is a transition element, but lead and aluminum is not a transition. I can say lead ion and aluminum ion present, or aluminum ion present. So we are not sure. I hope that makes sense. Now I will need to make a correction in the first one. Lead ion, aluminum ion, and zinc ion, all of them are amphoteric, so they dissolve in excess sodium hydroxide. Okay, so what that means is that even zinc ion is going to be suspected here. Now if I add a Ki aqueous solution, a potassium iodide, now because we are expecting, I know that it is lead, we are going to get a yellow PPT, a yellow precipitate. This yellow precipitate will now confirm the presence of lead ion. So lead 2 plus ion is confirmed. And that yellow precipitate is formed because of the presence of the formation of lead iodide. Okay? Because lead iodide has that yellow color. Okay, so that is it for that. Now we are going to look at what we have here. Something already have here. In this case here, action of heat. So the heat, this is the condition. You heat strongly. If you heat strongly, if the solid will turn yellow on heating and returns to white on cooling. Okay, we call that thermochromism. So a colorless gas will be involved. Definitely, I already mentioned that. And that colorless gas will turn lime water milky. Now, I separated in drops and excess. You don't have to separate this. On prolonged stronger heating, black charring of residue, smelling of burning organic matter. Now that's if you continue with the heating, which I doubt you are going to get to that point. Okay, so the inference, what you can infer from this is that yellow to white, that change in color already confirms that it is lead oxide, because lead oxide is formed, it changes from yellow to white, right? And that it is formed from lead carbonate, and the CO2 given confirms carbonate, right? And charring confirms starch. That charring of organic matter confirms starch. Then we have the action of dilute acid, dilute HCl. If you add dilute HCl in drops, you will get an effervescence, bricks bubbling, colorless gas, turns lime water milky, white solid partially dissolves. I already mentioned that earlier. So bubbling continues, that's in excess. The bubbling continues until solid fully dissolves. Solution remains colorless. So definitely we know that confirms the presence of, that gas is definitely CO2, confirms the presence of CO3 ion. This may not be among the first step, Then if it is iodine solution test, now this is one thing that I forgot. You are supposed to iodine. When you add a few drops of iodine solution, you get an immediate deep blue-black coloration. And of course, whenever you get a deep blue-black coloration, you know that it confirms the presence of starch, because the color of starch turns blue-black in the presence of iodine solution. When it is in excess, the color will intensify and does not discharge with excess iodine. That's very important. Then if you add aqueous sodium hydroxide, right? If you add aqueous sodium hydroxide in drops and in excess, you are going to get a white gelatinous precipitate will form immediately, definitely. And this white gelatinous precipitate confirms the presence of aluminium, zinc, and lead ion, right? Very important. And the precipitate dissolves in excess sodium hydroxide. Amazingly, the three of them dissolves in excess sodium hydroxide. So yeah, that's why I didn't bother doing this. So the three of them forms a white precipitate which dissolves in excess sodium hydroxide. That is very important. And I told you the reason, because the three of them are amphoteric. Now in the case of aqueous ammonia, you are going to get, when you add dilute ammonia dropwise and then in excess, a white precipitate to be formed, right? But this white precipitate does not dissolve in excess ammonia. It remains white. So lead and aluminium does not. As a matter of fact, this is what differentiates zinc from the rest. It is only zinc among all of them that dissolves in both in excess sodium hydroxide and also dissolves in excess ammonia. So we are suspecting a lead ion or aluminium ion present. So you can say lead ion or aluminium ion present. You write present. Okay, but this is not a confirmatory test. Now, but if you put a sodium potassium iodide test, if you to the filtrate from test 3, add potassium iodide solution, a bright yellow precipitate forms immediately, right? And in excess, the precipitate, because this is in excess, the precipitate persists insoluble in excess potassium iodide. That bright yellow precipitate is as a result of lead iodide, lead iodide, this should be PBI. That confirms the presence of Pb2+. That means it means that the ion we are looking at is lead ion. Then we have the barium chloride test. Okay, first of all, we dissolve in HNO3 and then barium chloride. I already told you that HNO3 can be used to dissolve the solution. In fact, if you want to separate it, add HNO3, it will dissolve the lead carbonate. Okay, then when you add barium chloride, a white precipitate is formed. I already told you the reason for that. Now, white precipitate does not dissolve in excess. So for the white precipitate to be formed, we are suspecting SO4 ion, SO3 ion, CO3 2- is present. Now, but since it does not dissolve in excess, okay, it confirms that SO4 is absent. It is consistent with carbonate salt or SO3. That means, or you can just simply say SO3 2- or CO3 2- present. Simply put. Okay, so from all of these that we've checked, we can conclude that specimen C is a mixture of lead-2 carbonate and starch. So that is it for that. Thank you very much. If you have any question, you can drop it on the comment section. I will be here to reply to them. Okay, see you in my next video.